Thank you. Thank you all for coming. Thank you for inviting me. Now we go from Australia to Australia again. Shanice was right. I don't know if you've ever been to Australia, but if you go there, so especially if you go to the east, to Queensland, so you come flying in and you think, hey, I've reached Australia, and then another 3 or 4 hours, man, it's just agony. Again, a random regression. So just to preface this, so the Grains Research and Development Corporation initiates this investment to look at basically improving variety selection using new analytic solutions. So we're doing this with University of Queensland and also University of Adelaide. And we're doing this within the context of national variety trials. So these national variety trials are key to farmers because it informs them for their cultivar choices within their own farm in their particular region. So we're looking at improving prediction of yield in new environments. We've been going at it from different angles. So within trial levels, we have like multi-trait approaches, longitudinal sampling using drone images, for example, but also at the network level between trials, trying to describe G by E, genetic progress over time, and then the use of environmental covariates to see if we can make sense of so how to classify trials sensibly into zones that could hopefully facilitate smarter allocation of cultivars to different regions in Australia. But we can use these covariates also to predict yield in new environments, as we've seen in previous talks. Again, Australia, of course. So we have the Australian wheatbelt, which is quite massive. The data spans the last, of at least 8 years, 2015 to 22. 153 locations, and basically covers the whole wheat belt from west and what they call south and north, which is actually north and northeast. So typically a trial contains 50 cultivars laid out in a row column design. So we spatially adjusted or corrected for the experimental design and extracted genotypic averages from those trials, plus the standard errors. We forward that to prediction methods. After a bit of filtering to get a bit more balance between years, we end up with 144 cultivars in these 935 trials. We also have access to environmental covariates, so I'm not going to bother you with details. It's a mixture of meteorological variables and crop growth model derived stress indices, and compared to these other crops for wheat, these crop growth models are actually quite advanced, so that's it's a nice feature. And we have several growth stages, so we end up with about 60 ECs. Some approaches opt to use all these EC and use some sort of penalization method to sort of cut down on the effects of unimportant or collinear variables. But we opted for a sort of pre-selection method where we just want to trim down the number of covariates to a manageable set of, in this case, 8. And this was done by Javier Fernandez, a colleague at UQ. Basically do some lasso approach across all these covariates for each genotype separately. And then we just look at the variation in responses to these covariates, and that sort of gives an indication of how important these ECs are for G by E. So now we have a selection of G by covariates that we think are relevant for G by E, and we can start. Yeah, I don't know. Let's see. Hey, there we are. We can start fitting models. So we all love mixed models, so we start fitting mixed models. So Y contains the blues for each genotype in each trial, and we have this standard errors to weight the whole thing. And the basic model that's typically used for these multi-environment trial data are the compound symmetry model and the factor-analytic model that we just saw. So we fit a fixed trial effect and then a random genotype and genotype by trial interaction. And in the case of the factor analytic model, we model the correlation structure between trials using this factor analytic structure. And for prediction, so we can do all kinds of fancy methods, also highlighted in Daniel's brilliant paper. Usually for prediction in a new environment with these models is basically the mean that you have in your observed set of environments is the best guess for what your prediction is going to be for a new environment. So if you want to go, want to be more precise, we need these covariates and we need to do smart modeling. I had a nice introduction to random regression, but to my pleasant surprise, everybody seems to be using random regression, and it's been introduced very well in this session. It was originally developed for time series data and mainly cattle breeding, but has been seeing increased use in G by E. And its basic form, it looks like this. So basically a standard mixed model, but we add a fixed regression term on a covariate X. And also an interaction, a random interaction between your covariate and the genotype. You can do that linear, but you can also do it with a quadratic term if the covariate calls for that. So basically you're fitting a slope for each genotype separately. And these, this genotypic deviation and the sensitivities are drawn from a normal distribution in a covariance matrix G, which holds the variances in intercept, slope, quadratic term, and the covariances between them. So here we're already estimating 6 components, and for many applications I found this is already pushing it. Models tend to be a bit unstable. Convergence also depends heavily on how you scale your X variable, so it's something you need to take into account. And also, since we're using raw polynomials here, they're highly correlated, and that makes the whole thing numerically unstable, especially if you go higher order. And a way around that would be to use orthogonal polynomials. I like to use Legendre polynomials because they're easy to implement and also quite easy to work with. Another general point is, if you're interested in doing more than modeling against a single covariate, you easily run into problems because this matrix grows larger and larger, and then your model fails. So the first thing we do is we switch from raw polynomials, which are typically used in the papers that I see. There are some exceptions, using orthogonal polynomials. And I've rewritten the fixed in the random part. Again, here it's basically the same thing that I wrote over here, but then there's this extra thing phi here, which is just the implicitly fitted phi matrix, which holds the Legendre polynomials. So basically this is the same, and now the V, so the genetic effect is held in this vector V, holding the coefficients for each genotype with matrix G as we saw before. So in this respect, nothing different to what we saw before. Well, then we can start generalizing across a number of ECs. So say we have P covariables, we want to model them all. In this case it's possible because we made a selection of relevant ECs, so there's no risk of overfitting here at the fixed level. So here we can approximate the mean by fitting a regression on each of these covariables, and we can even go higher order. So a linear, quadratic, and we can do the same thing at the random part, so we fit a genotype main effect plus an interaction with all these covariates. And then your variance covariance matrix looks like this. So here we have a variance in the intercept at the top, then the variance in slope, and the quadratic term for the first EC, and now we can continue for the variances in slope for the second EC and the third EC, etc. And then you end up with a very bloated matrix, which is actually unfittable. And that's where the sort of relationship with Daniel's brilliant paper comes in, because you can actually approach this matrix using a factor analytic structure on the coefficients themselves. So in this case here, lambda is the loading for the coefficients. So this term here represents the variance in intercept, and we have the variance in the slope for the first EC, etc. And you can try different orders of your factor analytic structure. And this pretty much works and converges all the time in my experience. So now we've opened up like endless possibilities. So here are these models again. So simple random regression on a single term, and in this case 8 terms. Looks a bit complicated, but it's not really complicated. But why stop there? So if you fit these models within a region, so you have a model for south, north, west, you can actually use the correlation between these coefficients to borrow strength from different regions. So you merge them together, you fit a region-specific intercept, as well as a response specific to each region, and you do a similar thing for the genotype effect. And now your G matrix becomes even more bloated, where we have this, as we saw before, for one region, you have it for another region, you have the full covariance between them. You can approximate it nicely with the factor analytic structure. How much time do I have? I'm going to skip this one. So what we do, so we have 8 years. So we opted for leave 1 year out cross-validation, which is the most challenging one because you have no information from that particular year. So you use all the other years as a training set and predict for the next year. This is just a snapshot of results. I'm not going to bore you with all the details, but let's suffice it to say that these arrows point at these random regression models, either fitted within a region, so in this case north, or fitted across all regions. And you see that they do quite a bit better in terms of accuracy compared to the compound symmetry and factor analytic model here on the left. And especially in the West in 2016, you see that this difference is quite striking actually. So it works quite nicely. And this is a summary table across all years, basically telling you the same. So basically, prediction accuracies compared to the compound symmetry increased by about 20%. And in this particular case, in West, it's nice that if we pair up information from South and West, West actually benefits from that. So we get an increase of a few percentage points in accuracy. This is just to show the difference in performance between the random regression model versus compound symmetry and how that depends on the environment. So in terms of accuracy, this random regression model all pretty much consistently performs better than the compound symmetry model. If you look at root mean square error, you see there's a strong environmental dependence. So in very dry years, we see a clear benefit of using the random regression model. And in terms of the root mean square error difference, so the precision with which you can compare varieties, we see also a strong interaction between regions as well, so region and temperature. So again, at the extreme ends of temperature, you see the clear benefit of using the random regression model, which makes sense because the prediction for the compound symmetry is a mean estimate for the mean environment, of course. So after fiddling with this model, I found it's actually a quite convenient way to use covariates and in a prediction setting. The model is quite accurate, it's fast, and it's numerically stable, and it converges almost all the time. I just made a quick reference to Daniel's paper. This would be equivalent to your factor analytic regression model, not entirely the same, but pretty much equivalent. And the fact that we fit these covariates as fixed effects as well, it means that we can estimate the trial mean, which is also a nice feature. And also you can very easily extend it to incorporate multiple structures using regions or year types, for example. A logical extension would be the independent factor analytic model. That's basically the stuff that Shanice just talked about. We're still looking into that. And also ways to make your environmental covariates more predictable. That would be, of course, the golden egg or the golden goose, whatever the saying is. So how can you sort of weight your predictions in terms of how accurate they are or precise? But that's future business within this project. For now, I'd like to leave it here, and thank you for your attention.